Welcome to a video on logistic growth. Let's take a look at our goals.
We're going to learn how populations grow, learn the logistic differential equation, and use partial fractions to find the solution of the general logistic differential equation. Now let's get started.
Here we have the two formulas needed when dealing with logistic growth. We have P of t, which is the population over time, and we have dP over dt, which is the rate of change of the population over time. As you can see by the graph over here, the population is growing very rapidly, but it soon starts to taper off. This is because every population has a limit, and this limit is called the carrying capacity. When solving for P of t, you must integrate both sides of dP dt, but this process is very long and tedious as you can see below, so we recommend you just know this formula. But for those of you who want to write this down, feel free to pause the video. Before we get started with some examples, I just wanted to clear some things up. When looking at function P of t, K is a growth constant, A is a constant determined by initial condition, and M is the carrying capacity. Using this, we can solve some of the most simple AP-style questions, such as, what is the limit as t approaches infinity of P of t? And what is the limit as t approaches infinity of dP dt? Take a second to look at the graph and think about this answer.
Alright, for those of you who got it, good job. But for those of you who didn't, these two problems could be made quite simple just by looking at the graph. Alright, so for number one, as limit t goes to infinity of P of t, so as we follow P of t along the graph, we can see that it gets closer and closer to m. So therefore, the answer to number one is m. For number two, as the limit t goes to infinity of dP dt, which is slope, as we follow the slope along the graph, we can see that it becomes closer to 0 as it increases less. So therefore, the answer to number two is 0.
One last thing to remember when dealing with logistic growth is that our population is growing fastest at half its carrying capacity. When looking at dP dt, we realize that there are two zeros at p equals 0 and p equals m. Using this and our knowledge of graphing quadratics, we can sketch a quick graph of what dP dt would look like on the interval from 0 to m. Looking at this graph, there's clearly a max at halfway between 0 and m. This is why a population is growing fastest at half its carrying capacity, and here's the calculus to prove it.
Alright, we'd like to end this tutorial with a quick example that could appear on an FRQ on the AP exam. Alright, suppose a population of butterflies is growing according to the logistic equation. If the carrying capacity is 500 butterflies, when is the population growing the fastest? So knowing what we just learned about carrying capacity, we know that the population will be growing the fastest at m over 2. And the problem gave us that m equals 500 in this case. So we know that P equals 500 over 2, which is just simply 250. So the population is growing the fastest when there's 250 butterflies. Alright. Thank you. Alright, so that concludes our tutorial. Good luck on your AP exam.